Okay, our next speaker is Yalan Song, and she will be speaking about high-resolution differentiable models for operational, national, and global water modeling assessment.
Hello, thank you. Thanks for introducing me. So it's my first time to be here, and very nice to meet you. So I'm Yalan Song from Penn State University. I'm a research assistant professor. So today I'm going to talk about high-resolution differentiable models for operational, national, and global water modeling and assessment. So the global and national water models are important tools for the prediction of flood, drought, water pollution, water scarcity. They can provide us with a real-time, high-resolution stream flow forecast and large-scale perspective on water availability and climate impact assessment. They also can support other applications. Now we're at the era of machine learning. It's changing the way how we do modeling. So this is a benchmark test for hydrological models on the standard CAMELS dataset we used pretty often in hydrology. So in this plot, the model performance from the left to the right getting better in terms of the Nash cycle efficiency score. So here is our traditional process-based model, and here is the LSTM model. So we can see there is a performance difference between these two types of models. So the question is, how can we use machine learning tools to improve our global and national water model? In this, one of the biggest challenges in global and national water modeling is large-scale, high-resolution parameterization. Since in these two types of models, there are a lot of process-based modules and routing modules included, and include a large amount of parameters need to be calibrated and regionalized. So how can we use which can be very difficult. So how can we use the big data and the machine learning tools to help solve this problem and improve the model accuracy, efficiency, and overall capability? The one solution is differentiable modeling. That is a framework hybridizing machine learning and process-based models. It integrates those two types of models and trains them simultaneously on the big data. So inside of this framework, the neural network can be firstly used for the parameter regionalization. That is to find out the relationship between the big data, for example, the forcing and the attributes from all the basins and its relationship to the parameters of the physical models. Another way of the neural network in this framework is to replace those complex and unknown modules to help us for the knowledge discovery. And this framework is trained on the GPU, and so it can learn from the large-scale data set like the neural networks. Most importantly, it has a physical model embedded. So the physical models inside the framework will directly do the physical simulations for us to maintain the full interpretability of this framework. So it's not a black box like a neural network. Now it's an open box. We can clearly see those processes simulated inside of the framework. Recently, differentiable modeling has making a lot of progress. We have some work in our group, and also other researchers making a lot of contributions to this topic. Let's come back to the CDF, the benchmark case again to see where the differentiable models. So we have a different version of differential models based on the different type of lumped hydrological models. For example, we have a differentiable HPV 1.0. That is our first version of the differentiable hydrological model. And then we have an improved one DHBV 1.1, PD6, DPRMS, and an ensemble of different model structures. All those models, all those differentiable models have similar performance as you see those curves clapped together as an LSTM model. That means differential models have the similar accuracy as the neural networks. And yesterday there was a very good question asking about how is those machine learning models in those extreme events that is not showing in the training data set. So here we're also curious about how differential models, what's its actual population capability that can decide how much we can trust on this model. So we designed the exploration test in the untrained extreme events. So in this test, what we did is we only trained this model with smaller events. For example, those blue time series shows here, and then we removed those large events from the training data, like those green time series are hold out and removed from the training data. And then we tested this model in a separate and continuous time series, like the orange one here. So with this way, we can show like how this model in those extrapolation tests. And this is a result of the absolute relative error of the annual peak flow. Lower the better. So when the return period is smaller, like it's less than 50 years, from 5 to 50, we can see the performance of the LCM and differential models are very close to each other. However, with the increase of the return period, when the return period larger than 50 or 100 model, those two type of models has more difference in their performance of the prediction for the peak flow. The differential models has a lower bias, lower errors. More specifically, we found out that differentiable models reduced 80% of the events. They reduced the 80% events at peak error and reduced the 40% of the events for more than 10% in terms of the peak error. So why differentiable models has such good capability compared with the LSTM? Let's look at one example. This is an example of the events with a return period larger than 700 years. So the green line is a simulation of the LSTM. Its peak prediction is exactly same to the maximum value we used inside of the training. So that's shown by the black dash line. Since LSTM is a neural network, it has difficulties to provide the prediction outside of its training data. But differentiable models is still process-based model, so it can respect the mass conservation. And more than that, it can so when it can respect mass conservation, when it receives a large precipitation on the peak day, it can give a larger stream flow response. But more than that, it also can consider the interactions between the process. For example, the contribution of the snow melt to the stream flow. Since in the process-based model, there are a lot of physical states that can record those large long-term variation due to the, for example, due to the snow accumulation and the melting. So those are the reasons why the differential models can have a better performance than the LSTM in this extrapolation test. And in Feng et al. 2023, they also demonstrate that differential models can have a good extrapolation capability in space. So what they did is like hold out the training data from the in the whole region and then test the model in this holdout region. So in this way, they validated that differential models can have a better extrapolation capability than LSTM in space. One important, very good advantage of the differential model is it can provide us with untrained variables. Since it's based on the process-based models, there are a lot of intermediate variables simulated inside of it. So based on this, we can have the predictions of the untrained variables. For example, like groundwater recharge. So in this modeling, we use the lambda differentiable hydrological model based on the PR mass. And it integrated with a temperature model called SN-temp. In this way, we can use both stream flow and temperature model to train it and then test it for the intermediate variables, groundwater recharge. We compare the simulations from the differential model and the observation. We get a low bias and a higher R2 compared with the global hydrological model, for example, water gaps here. Based on this, we did a long-term trend analysis, for example, 50 years trend analysis under different emission scenarios. And here is the result of the median emission scenarios. So the differentiable models provided a larger recharge predictions than the ensemble of the global hydrological models on CONUS. So this work is under preparation. I think it's going to submit it very soon. Then now we have introduced the differentiable models can be used for the hydrological models, which is based on the ordinary differential equations. Can we use it for the complex partial differential equations? For example, two-dimensional shallow water equations. Yes. So in this case, we integrate a neural network that is to use the input like the water variables, the water depth, velocity, and the roughness to predict the magnesium, which is the parameters of the two-dimensional shallow water equation. So we train this framework, we can get the relationship between the input and the output. Since we do not have the observation data of the simulated velocity and water depth, so in this case, we used the numerical models to create a synthetic case. In the numerical modeling, we firstly pre-describe a distribution of the roughness and then pre-describe the relationship between those between the water variables and the roughness and its relationship with the friction, that is our magnesium. And with the simulated velocity and water depth, we use it as a target to train this whole system. Now we can see if this neural network can recover this relationship we pre-described in the numerical simulations. So here is a result. Let me show the animation here. Okay. Okay, so with the decrease of the loss, we can see the magnesium predicted by the neural network is identical to the one we predicted in the empirical formula. That means this neural network can reconstruct the relationship we pre-described in the numerical simulation. And this is a pattern of the relationship between the friction and the Reynolds number and the roughness from the empirical formula, and this one is reconstructed by the neural network. So those two looks identical. That means neural network now can simulate, can learn those relationship we used in the numerical simulation. Then, so now we have introduced the differentiable modeling can provide a high accuracy and it can provide the prediction of those untrained variables can be used for complex models. How can we use it for national water modeling? Those hydrological models we mentioned in the previous slides, like HPV, PRMS, and SEXMA, those are lumped models. They use the basin averaged input to provide the prediction of the stream flow at the downstream of the gauge. However, for national water modeling, there will require the stream flow simulations that is high resolution and is available everywhere inside of the whole river network across the nation. But the lumped models cannot do this, can only provide the point prediction at the downstream of the gauge. And the other disadvantage of the lumped model is it does not consider the sub-basin heterogeneity for large basins. For example, if we want to provide the prediction for the downstream of the Mississippi River, the lumped model requires the basin average input across half of the United States. So this will cause a lot of errors in the simulation. And other problem is the scaling issues. Since the observations of the stream flow is from the gauges with different scales, most of them are very large scales. If we directly train our model on this scale and then later on we want to further apply it to the unit basins for the routing, there is a scaling issues between the model training and testing. So because of those challenges, in this year we proposed a high-resolution differentiable models for national water modeling. The idea of this work is based on the scale-dependent parameterizations at the sub-basin scale. This means we will use the high resolution of the input at the unit basins and then provide to estimate those parameters at the unit basins, and then we conduct the rainfall runoff simulations with hydrological model. For example, HPV here to simulate the runoff at the unit basins. Then we integrate a routing model to have the simulations of the stream flow everywhere inside of the whole river network for the basin. So this model is a high resolution one. We call it DHBV 2.0. Then we use a high resolution input from the big data, like all the forces and attributes at the unit basins, and then train this model on the 3,000 gauges. Once this model is trained, we can have a neural network represent the high resolution relationship between the high resolution input data and the parameters for the unit basins, and is applicable to the whole domain. So with this model, now we provided a 40 years stream flow data set that is seamless on the Mary River network with a 7 kilometers median river length. And then we also provide other hydrological variable simulation like the ET base flow in more than 180,000 Mary unit basins. Then we also evaluate this model by comparing it with the LSTM and current National Water Model 3.0. So here is the performance performance curve of the LSTM and the differentiable models. They club together means they have similar performance. And here is current National Water Model 3.0. We found out that the differentiable models improved the simulation of the stream flow on 4,000 gauges. Then let's look at some extreme events captured by this model. So we look at the two hurricanes in 2018 and 2020. So the colored part shows the regions that is under effect predicted by the model under effect of the hurricanes. The red colors means the stream flow has a very low exceedance probability. That means the magnitude of the stream flow is much higher than the history records. And this is the real trajectory of the hurricanes. See these two, the patterns matched, predicted by the model matched well with the trajectory of the real hurricanes. That means the differential models can well predict those extreme events. Then we further improve it for the operational purpose. For example, for the next generation of the operational national water modeling proposed by NOAA, they proposed a high-resolution river network called hydrofabric that is much denser than the river network we use in our paper. But here we can see the in these two types of river networks, the differential model 2.0 has a similar performance. That means now it can be integrated in the next generation data pipeline of the national water model. And we have except from besides the HBV model, we also have the ZEXMA and the PRMS model high resolution versions being implemented. Here shows the parameters pattern learned by the neural network across the corners. The left one is a shape coefficient from the rainfall runoff model HBV that is related to the infiltration process of the rainfall runoff process. And the other one is a Mannis coefficient from the routing models. Those are the patterns learned by the neural network from the big data. We further use this model for global water modeling. We train this model on 4,000 gauges on globe, as shown here by the dots in this map. Then compare it in the trained gauges and untrained gauges with GLOFAS. So here's our differential models, and here's a GLOFAS. Then we further tested on the large rivers. We only trained this model with a small and medium-sized catchment, and we tested on those large natural rivers and the mixed rivers with the human impacts. So the last row is the performance of the differentiable models in the simulation of the mean annual runoff. It can provide the high R2 and lower bias and lower RMC compared with other global water models here. That means differentiable models can it will explain the spatial variability of the annual flow and the interannual variabilities. Based on this, we did some trend analysis for the fresh water for actuaries. This is an actuary in the eastern side of the United States, Chesapeake Bay. We calculated all the input flow, all the inflow going to this actuary and aggregate them to compare with the observation data for the Chesapeake Bay. So here is a comparison. I would say they matched very well. And then we did a 20 years trend analysis for the actuaries in the United States and Europe. We found out that the simulation shows that in the eastern side of the United States, we see an increased trend for the fresh flow going to the actuaries, and on the Europe side, we see a decreased trend. This work is submitted I think last month. And then we further use this model for the prediction of hydrological signatures. For example, the monthly runoff autocorrelation, that is a correlation between the time series and its lagged values. For example, here 2 months the lag. And then we also predict the elasticity, that is the ratio of the stream flow, seasonal stream flow to its precipitation input. Then we compare the simulated signatures with the signatures calculated from the observation. Differential models is the only one that can provide the R2 larger than 0.5. It's around 0.7 here. So that means differentiable models also can help us to capture those hydrological signatures. In this work, we will also provide a global hydrological data set. And then this is the result of the seasonal electricity in globe on those unit merit basins. So here are the takeaways for today's presentation. Differential modeling eliminates the performance gap between the process-based model and pure machine learning model. It transforms the large-scale, high-resolution parameter calibration to parameter learning from the big data, represent a step change in the high-resolution hydrological simulations. So as a side topic, I also want to introduce you the foundation model. So the foundation model is a model that based on the large language model trained from the big data. It can provide the multiple variable predictions simultaneously. And here is a foundation model from our group. You can see the foundation model performance is similar or even slightly better than those models trained from the single variables. So if you ask me, like, if which one is a future model, like a foundation model or differentiable model, I don't know. So that's my answer. Yeah. And at the end of this presentation, I want to do a quick announcement about our AGU sessions. We work on the submissions from the early career researchers who are working on the AI and big data in hydrology, and we also work on submissions about frontier AI models like large language models, LSTM models. So thank you.
Thank you for that talk. We have time for one question while we switch speakers. That was really cool.
Thank
So
you.
clearly from your slides, the differentiable model is performing well and better than the physically based models. Is there a way to pull physical insights from this type of modeling to improve models like the National Water Model?
Yeah, this is a very great question. So, so compared with the traditional process-based models, differential models, yes, has a better performance, but it's not pull physics from the traditional models. It's directly integrate the traditional process-based models with the neural network. As long as you can make it differentiable, that is like you can make it use those like the PyTorch, those language can support you track the gradient. Differential means we can track the gradient. So in this way, you can train the process-based model like the way how you train the neural network. And it's paralleled so you can use the big data. It's different from those traditional models. This calibrate the parameters like side by side and basin by basin. Since you can take advantage of a large data set, and you also can use neural network to predict those parameters for you. So both sides, like one side is the parameters well calibrated, other side is paralleled on the large scale data set. So both sides can help you to improve your model performance.